Good day and welcome back to the second part of our discussion of double integrals in polar coordinates. So let me just start off with a few quick highlights from our previous video. If we have a point sitting in the, typically we might think of as the xy plane, this y coordinate measures how far the point is from the x-axis, whereas the x coordinate measures how far the point is from the y-axis. An alternative way of labeling each point with a coordinate system is to instead think of it as having coordinates given by r theta, which is the polar coordinates for the point, where r is a positive quantity representing how far you are from the origin. Theta is this angle you get coming up from the positive horizontal axes going in the counterclockwise direction. And remember kind of the key relationships are x is r cosine theta, y is equal to r sine theta, and from the Pythagorean theorem, x squared plus y squared is r squared. Furthermore, we went on to talk about evaluating integrals over what we would refer to as a polar rectangle. That is to say, those polar coordinates r and theta are both bounded by constants. And remember, polar rectangles don't necessarily look like the typical rectangle you might imagine, but they're typically things which are circular and symmetric about the origin. And how we evaluate such an integral is we convert each x into polar coordinates, r cosine theta, each y into polar coordinates, r sine theta, and then remember the new and more subtle part, dA becomes r dr d theta, so make sure to remember this extra r which is introduced. The r values for our limits of integration vary from a to b, the theta values from alpha to beta. And let's now investigate this formula by looking at some nice concrete examples. For our first example, we will evaluate the double integral of the function xy over the set D, which is a disk centered at the origin with radius 3. And as I've mentioned previously, I will always request that you sketch a picture of your region for integration, and in fact when it comes time for the exams I'll just make that part of the wording. So a disk centered at the origin with radius 3. And note, this is the example that we started off with back in our previous video. And I just want to note at this point, no instructions have been given in terms of how to evaluate this double integral, and we certainly have the choice and the ability to go back to our previous methods using Cartesian coordinates, or you can view this as one of these type 1 or type 2 regions, which we've certainly done similar things. It's just not all that convenient. The better observation to make is that this is a polar rectangle and can be evaluated very efficiently in polar coordinates. To describe this polar rectangle, what we would like to do is indicate how are the r values varying and how are the theta values varying. Note the r values, think r equals 0 puts you at the origin, and the r values vary from 0 all the way up until you hit that outside circle, which is r equals 3. That is to say 0 to 3 for the r values. And because we are going all the way around the origin, the theta values would vary from 0 to 2 pi. And we now have everything we need to sit up and then evaluate the given double integral. So the double integral over this set D of xy. So note, each x becomes an r cosine theta, each y becomes an r sine theta, and the dA becomes r dr d theta. On the inside we have r varying from 0 to 3, and on the outside theta varying from 0 to 2 pi. And once we get it to this point, this is really kind of an old problem. It's an iterate integral that we need to evaluate. And a few key observations. Note, because our limits of integration are all numbers, the order is irrelevant. We could have gone r d theta dr, as long as we changed our limits appropriately. Similarly, what you might notice is that the function we are integrating separates into a function of theta, cosine times sine, multiplied by a function of only r cubed. So we can immediately break this up into two separate single integrals multiplied together. The first one would be in terms of thetas. We have a cosine theta and a sine theta. And the second one, in terms of r, we are integrating r cubed. And beginning with this left integral, I guess I'll note the technique of integration that would be the most efficient is a substitution. And note, you could choose u to either be sine or cosine, but simply to just avoid negative signs, let's go ahead and let u be sine. So we do this work to the side, so that du would be cosine theta d theta. So the cosine theta, the d theta, becomes du. And then we need to change our limits of integration. Note, when theta is 0, our lower limit of integration, u is sine of 0. Similarly, when theta is 2 pi, the upper limit of integration, u is also sine of 2 pi, which is 0. That is to say, we have the integral from 0 to 0, u du, multiplied by, and I'm not even going to bother with the second integral, because if we think about the value of this first integral, whenever we integrate from a number to that same number, we simply get back 0. And 0 multiplied by anything is in fact 0. And just to double check, the fact that this double integral is 0 implies what relative to this original double integral? Remember our interpretation of the double integral as a net enclosed volume. The fact that we're getting back 0 is just indicating that the surface corresponding to this function, z equals xy, encloses the exact same volume above the z equals 0 plane as it does below the z equals 0 plane when you are on this disk D. And before moving on to our next example, let me also make the observation that we did not have to tell you to use polar coordinates. We just immediately jumped into polar coordinates, I guess for one, because it's our topic of interest for today, but secondly, because of the region we are describing. This is much more inconvenient to describe with Cartesian coordinates, as we've seen in past examples, but in terms of polar coordinates, it becomes much simpler. So let's move on to a second example. Let's evaluate the double integral of cosine of x squared plus y squared, where r is the region above the x-axis and in the circle of radius 3 centered at the origin. So the first step is going to be sketching our region of integration. So it's essentially this region enclosed, call it R, by the top half of a circle of radius 3 centered at the origin. And note once again, there's no instructions in terms of what method to use, but we have this polar rectangle, i.e. circular symmetric about the origin. So polar coordinates seems like a great choice. And whenever we see a region of this form, I would strongly encourage you to begin your attempt with polar coordinates. And in polar coordinates, I would describe this as saying the r values are varying from 0 to 3, just like our above example, but our theta values, since we are only going halfway around, we start off at theta equals 0, and we rotate around to theta equals pi. So with this in mind, the double integral over r can be simplified sufficiently. Note that x squared plus y squared very nicely converts into polar coordinates as r squared. That is to say, we end up with a definite integral of the cosine of r squared, and dA is r dr d theta. Our limits of integration, r on the inside, theta on the outside. And again, let me make a few observations. Because our limits of integration are all numbers, because we're integrating over a polar rectangle, we could change our order of integration to whatever is the most convenient. But furthermore, note that the function we are integrating is only a function of r. That is, it's a function of r times 1, which is only a function of theta. So we can immediately, again, break this up into two single integrals multiplied together. And not only are they two single integrals, they are two very reasonable single integrals to evaluate. The antiderivative of 1 would just be theta, and we're talking about from pi to 0, we simply get back pi. In terms of cosine of r squared times r, let me note that the antiderivative would be 1/2 sine of r squared from 0 to 3. And if this is something where you look at it and you recognize the antiderivative, I'm 100% okay with you writing that down. If not, note that you can make a substitution. If u is r squared, then r dr is 1/2 du. So you see where this 1/2 comes from. We substitute in 3, we put a minus sign and substitute in 0. So we would have 1/2 sine of 9 minus 0, because the sine of 0 is 0. And this number we end up with is the value of the double integral, which completes the example. In our next video, we will continue our investigation into double integrals with polar coordinates. Stay tuned and take care.